This is going to be the lecture about of the introduction to the line integral. So let me first explain about the motivation I came up with. I think it's a really natural one to consider. So here's think about this as a giant field and really wide, and each position, the condition of the ground is different, so construction cost varies. So this is going to be the construction cost of the road per feet, for example. So that's the condition. If I'm looking at this spot right here, maybe it has a very rough spot, the construction cost is more. Maybe down here is very soft and easy to do the road construction, so maybe it's a slightly cheaper, something like that. So suppose we have a path, we're going to call it C, the path C, and if you decide to construct a road along this path, and however you figure this out by the Cartesian equation, whatever, the what we want to calculate here is the total cost of constructing this road along this path. It's, let's say that was our question, how are we going to compute that? Of course, these things are, at each position along this curve C, the construction is changing. That this is a typical Riemann sum idea. So suppose this is a segment, a zoomed in segment of this curve C. Suppose we divide it into many pieces, and this is k minus first position, and this is the kth position. This is very close to each other, the typical Riemann sum assumption. So we pick one point in between. Let's say that was xk star, the usual sample points, yk star. So because they're close to each other, we assume the construction cost is the same for this path, and that we're using this sample xk star and yk star. So construction cost would be fxk star and fyk star. That's the construction cost. But we're doing that for this much of the length. We're going to denote that by arc length s, sk. So the delta arc length sk. So let's denote that as tk. That's the cost of construction along that path, pk minus 1 to the pk. All right? So we have to add this all up, all the way from the very first interval to the last interval to compute the total cost. So maybe this is reasonable. The total cost is probably very close to sum of all these things that we have written down over there as a tk. So this unit cost times delta sk is probably the close to the total cost. So this is a typical Riemann sum that's appearing here, and we've seen that a lot recently using, whenever we calculate the double integral, this delta ak showed up, and for the double integral, and when we're doing a triple integral, this delta vk showed up, triple integral, and so on. Every time when we had that, we use a different parameterization to rewrite this delta ak and delta vk in terms of this parameters. So that's what we're going to do to compute this one. But this idea itself, whenever we consider this double integral and triple integral like we did it before, we introduce a notation. So this is a slightly different idea. If you think about all this integral we have seen so far, this is still a slightly different idea. So if this exists as a value of t, no matter how you divide this path and whatever sample point you choose, if it is always a common value, that common value is denoted by this, the integral and the subscript c and f of xy, and we use the symbol ds. Okay? So this is called the line integral along line integral of f of xy along the curve C. So that's the name of this integral. It's not pausing, so let me go on. So that's that. That's our very definition. And next goal is that actually how we're gonna, let me look at my note. So the next part is titled and parameterization and Jacobian factor. So why don't I go to the next page. So I decided to stay in this page. So it's a parameterization and Jacobian factor. So I want you to look at that Riemann sum, and when we parameterize all this curve C, the x and y will be obviously, written in terms of t, but delta sk is something you have to think about. So here first we have this curve C. It has the beginning point and end point in here. That could be P and Q, x and y coordinate, but we're parameterizing, so when we parameterize it, it has the initial t value and terminal t value. And each of the position in there, let's say that in between, we have t equals tk minus 1, and that will be this point right there, and t equals tk, and that will be that point over there. Okay? So we have many points of division in there, and then we have a sample point in between. Okay? So we have parameterization, x equals xt, y equals yt. That's our parameterization. So how are we going to calculate? The whole goal is just calculating this delta sk. All right, if you don't remember how to calculate the arc length, you should look up your early chapters and recall that how we calculate the arc length. It was this. So we have a parameterization. It's arc length in between tk minus 1 and tk. So we write the parameter tk minus 1 and tk there. And then we calculate something. So what could that be? Inside, there are different versions. You can use this xt and yt. I'm bracketing there. There's a version that uses that. But there's also a version that uses this position velocity vector r prime t and its absolute value. Okay? So where r of t is this position vector xt, yt of course. Okay? So that's kind of nice version, abbreviated version. So what we're going to do is that we're going to rewrite this one in terms of delta tk, right? The goal is that the idea of the Jacobian factor is that how we're going to write this delta sk in terms of delta tk. How is this related? What is the stretch factor? Okay, so you might already know that recognize this as a mean value theorem applies here. So if you don't remember how the mean value theorem applies to this integral form, you have to write it like this. So you break this integral into this form. I'm going to abbreviate it just r prime dt and continue like this. So I'm going to explain what this is. It means we're integrating on this side here from tk minus 1 to tk. But on the right hand side, we're integrating from tk minus 1 to a. Then we're integrating a to tk. That makes perfect sense, right? If a is in between tk minus 1 and tk. If you're going from 1 to 5 integral, t value goes from 1 to 5, you can go 1 to 2 and 2 to 5. That makes perfect sense. But we formally extend the integral even if the lower limit is greater than the upper limit. With that extension, even though a is not in between tk minus 1 and tk, that formal extension allows us to break this integral in this way, no matter where a is. So once you write it like this, you can rewrite it into a typical mean value theorem form. So the first term stays like this. The second term will turn just like the first term, where the t goes up there and then it goes down. That whenever you swap this upper and lower limit, there has to be a sign change out there, and that's how we extended the definition of the integral when the lower limit is greater than the upper limit. All right? That looks just like the typical mean value theorems. To apply the mean value theorem, if you still don't see it, we have to look at these integral function as a function like a gt is going to be this a to t r prime dt. So if you recognize this as a function of t, so you've seen this type of function in fundamental theorem of calculus, not this absolute value all prime part, but the where t appears and how we treat this one as a function. So let me go to the next page. So let me continue. So where am I? So it's here. All right, let's recall the mean value theorem. So mean value theorem says, well, let me first copy the delta sk over here. So far we have gone up to this much, r prime and dt, and this we wrote this gt like this, right? R prime and dt. So let's recall the mean value theorem. Mean value theorem says that applied to gt to these 2 points tk and tk minus 1. So g of tk minus g of tk minus 1 divided by tk minus tk minus 1. This, called the quotient of difference, is actually exactly equal, not approximately, exactly equal to some value of a derivative. So that would, where we'll write a tk hat, for example, like this, where this t k minus 1 and tk is in between this tk minus 1 and tk value. So that's the mean value theorem. And we write this tk minus 1 and tk minus 1 as delta tk, right? So recognize this part here, I'm going to write underneath it, is a gtk, and the other term over right here is actually g of tk minus 1. So we know that part. So we want to look at this quotients of difference, realize that the numerator is exactly what the delta sk is. So if you solve for that delta sk, we multiply the delta tk to the g prime stuff. So from there we know delta sk is g prime tk hat times the delta tk. So here it is. We pull out the delta tk, the usual thing that we do, and we wrote this delta sk we're multiplying as a delta tk times something. So that must be the Jacobian factor of this situation. We must call that as Jacobian factor of this situation. So let's rewrite this g prime of t, k star. What is g prime of k? So it's by fundamental theorem of calculus. If you look at in the very first line, at the end of the first line, I'm putting this arrow right there. So that's our gt. So fundamental theorem of calculus said it is, if you differentiate that one, it's going to be just inside function with our t in it. So this times a tk and a hat. So that's the function. All right, tk is a special. I'll write it down. It's a special value. And when we write the Riemann sum, the star is just an arbitrary value, right? So we can choose those star. So let me write it here. Choose those tk star to be this tk hat, right? Then Riemann sum, is just stated nicely. So let's go back to the Riemann sum. So here's the Riemann sum. K going from 1 through n of that f of x, now this time is x of t something, right? And then we chose this value tk star is chosen to be that tk hat, y of tk star times delta sk. That was the very accurate total construction cost, right? But we're writing this in terms of, so here's the s xtk star ytk star times delta sk is now this, if you look at this part up there, where I stated Jacobian factor, the g prime of tk is now, it has this form with a star, because we wrote it as star now, r prime tk star, and then there's delta tk. All right, this tk is a usual thing, right? It's really tk minus 1. So this is the one variable Riemann sum that we have learned in the calculus 1. Okay, so this will approach, not equal to, will approach following a t varying from a to b. If you go back and see that part where we parameterize, it's going to a to b, and f of this x and y is written in terms of t, and then Jacobian factor is absolute value of r prime t. These are all t's now, and dt. So that part here is just one variable scalar function of t. So it's a Riemann sum in one variable. So this is actually how we calculate that line integral. So let me summarize it here. An important formula: if you're looking at the line integral, the notation is suggesting this is a line integral. If you're looking at this line integral, then it is equal to actually one variable integral, xt, yt, whenever you have a good parameterization, rt and dt. So that's the formula. It's an important formula. This is actually how we calculate that line integral of f along C. The interesting part is that this one has nothing to do with the parameterization. So there's no parameterization. Does not involve any parameterization to define this left-hand side. But the right-hand side here is about the parameterization. You can see if you parameterize different, then x and y, it will be a different formula. And r prime t will be different formula. Therefore, its absolute value will be different formula. Altogether, somewhat, it should be the same thing. All right? So right-hand side kind of depends on parameterization, but left-hand side says it actually doesn't matter. So that's the one thing I'd like to say about this formula, and that's how we actually calculate it. So remember, the Jacobian factor here of the line integral is absolute value of r prime t. So let me add the typical explanation about the Jacobian factor here. What is Jacobian factor? Is that we are looking at some sort of bent object here. This has been all the same for the double integral and the triple integral, and then you will see again and again. So this is actual C, and here is actually T line. So as T varies from, for example, T2 to T3, and T4 as well, spaced like that. So we have this delta T without K, subscript, and this is T line. This is what is happening to the T part, but these T2 and T3 correspond to this T equals T2 and T equals T3. Maybe T equals T4 is not well spaced. They are close to each other, and distance T2 to T3 over here in the T line is not going to be equal to the arc length here you see from T to T3 over there in XY plane, right? But what the Jacobian factor is saying is that if you're looking at T2 to T3, that has delta T, which is delta T3 minus T2, then what you see over here is that this arc length right here, we denoted by delta S2, is not exactly delta T, but there is a stretch factor, kind of stretched, and by factor of 2 or factor of 1/2, something like that, stretch factor is absolute value of L prime T. That's a velocity vector there. Okay, so if this case here is going to be roughly T of, let's say, is 3. Okay, so that's the meaning of the Jacobian factor. It's an important phenomenon in integral business. Right? This is going to be the geometric interpretation of the meaning of line integral. For example, I'm going to draw this top part. This is going to be the graph of z equals f of xy. That xy plane we've seen before in the construction example, construction cost example, is this plane down there. So we're looking at this type of thing. Okay? So the top part here is the graph of z equals f of xy. Bottom part here is xy plane. Okay? And suppose we have the curve C down there. Curve C. So that's a curve C. The meaning of the line integral we defined there of f of xy along the curve C, which is denoted like this, could be the following. So I want you to look at this curve in the xy plane and look at this endpoint and go and find the corresponding z value up there. And also find this line, the curve down there, and see for those xy value, you find the z value up there. Okay? So this is kind of a graph of z equals f of xy restricted to the points on the curve C. Then find in each point here, let's say, let me go ahead and put some points down there and then draw this vertical line underneath it, directly underneath it like this. Okay? Then by sketching like this, you can see we've kind of visualized this curtain. So the curtain is a good word for me. It's a curtain. All right, what does this represent then? Is probably the area of this curtain. All right, like we did before, if you look at, the fine division of this curve C into pieces, where each piece corresponds to these t values, and then you go up there, I suppose relatively tall, something like that. So assuming this is almost a straight line, and it's just close enough, straight line, close enough such that the top part is also, the straight line. So we're just calculating, so that will be some sort of sample value, roughly. Yk star, where this yk star is underneath it. So if we assume the bottom and top is almost straight line, and this meaning of this f xk star, yk star, times delta tk would be the area of this rectangle. And we're adding all this up. Therefore, this could be the area of the curtain. I think that's kind of natural. So that's a one different meaning, and you will see in the later this vector field example of that. From there, this line integral rises again. But I think these two things are sufficient example, so that we can do some examples, actual calculation problem. Okay, so let's look at some example. All right, suppose we are given, let's say that construction cost function is 2 plus x squared y, something like this, and this is against this line integral along this curve ds, and where the curve C is given by upper half circle, so this is y-axis. So C is this curve, not the region bounded by x-axis and this curve, just this curve part here. That's what it is. And it is a part it's given by x squared plus y squared equals 1, and maybe y greater than equals 0, this additional condition will solidify to make this precisely describe this circle that is sketched here. Don't think that because of this condition here, y is greater than 0, we're looking at the upper half disk. This is not a disk, it's just that circle part. So before we actually compute or think about the meaning of this, is that, and this 2 plus x squared times y could be the construction cost, and then whenever you are constructing over here the north pole part, which is 0, 1, I just filled in there. The construction cost is going to be a certain amount, which is actually 2. Down here is 1, 0, and negative 1, 0. They're also 0. But you can imagine other points in between x and y are not necessarily 0. Therefore, we have some positive construction cost going on there. So the beginning of computing this one starts always with the parameterization. Because this is a circle, there's a standard parameterization, but many of you will do that standard parameterization. But if it is not like this, some of you have a different idea about parameterizing the curve, and possibly look like a different formulation of this line integral, but they're all supposed to end up at the same value. That's the interesting part. So let's use standard parameterization. It's a circle with the radius 1, so it's going to be cosine t, right? And y equal to sine t. So that's a good parameterization, but you always have to find this t value. How is this t is varying? If it is not clear, just go and plug in some of the value. That always gives you some idea. So why not t equals 0? And it turns out t equals 0, I'm going back to this graph of c in the xy plane. And here, this turns out to be t equals 0. Okay? So t equals 0 makes it cosine 0, 1, sine 0, 0. If you do the same thing with the t equals pi, then that part here is t equals pi. So if you plug it in there, you can verify. You might pause the video and verify this fact yourself. So I'm putting also into that picture an arrow. And this is the orientation. That's as t increases, and we are parameterizing this curve along that direction. So we got all this, right? We got the change of variable. So we always compute the Jacobian, right? This r prime, the absolute value of r prime t, which is square root of derivative of cosine is negative sine t squared. Derivative of sine is a cosine t squared, right? All the way up here. But you can see this is 1, and if it was because it was a circle and typical parameterization, doesn't have this Jacobian one, right? So let's go to the integral, the line integral of 2 plus x squared y ds, example, is equal to this one variable integral from 0 to pi. That's the parameters, the beginning value and the terminal value of the parameter, and all these x and y is replaced by cosine t, and y was a sine t, right? It's a squared and a sine t. So that's this f of xy part in terms of t. Then we have to multiply Jacobian, which is 1. Then it becomes just dt. Okay? So this integral has a nice substitution, because derivative of sine, cosine here, is negative sine t, so it is up to a constant multiple, so the u substitution will work. So let's make u equals a cosine t, and I want you to pause the video and do the computing the antiderivative method and get the value for this integral and see if you get the same answer. Okay? Now, to see me doing now, so we're going to find the antiderivative. This is a substitution with the u. So that changes. So this is how I do, and if you have a different way of doing it, that's fine. So Because dt is what we want, right? dt is going to be replaced by du, so you write a du here. The derivative of cosine t is negative sine t, but this substitution rule works like this. It's always reciprocal. If you do this, we use substitution. When you're writing something you see inside this integral to something else, creating a new variable, this reciprocal is how it works. Okay, so the first part is, if you look at the 2 part there, it doesn't have any cosine or sine, so I should have separated that one first. So here's a 2 dt plus the second part has cosine t and sine t. So that part we're doing substitution. Now this one being u values, not the t values. So when t equals 0, u value, because it's y equals cosine t equals 0, the u value is 1. When t equals pi, u value is negative 1. We got rid of that 2. We already calculated here, so we're doing the other part. So cosine t is now u, so it's going to be u squared in there. And sine t is still there. I'm not trying to rewrite this one in terms of u because we know it cancels with a t. Alright, I assume you knew that much. Right, du here. So these sine t canceled, and that's why this integral works nicely. Here's a 2 dt. Let me just get rid of this and calculate this one. This is going to be just 2 pi, right? And plus, this whole thing cancels. There's negative out there, and so you see the 1 is down there and negative 1 is up there. It's not quite a right order. So if you flip it, and it becomes positive again. So negative 1 and positive 1, and sine canceled, and u squared du is the integral. So it's a 2 pi plus the antiderivative of the u cubed between 1, negative 1, and positive 1. So that's 2. So it's a 2 pi plus 2 over 3. Seems like the value of this line integral that we looked at. Okay, this is how you do it. Sometimes this last bit where you have to do this one variable integral, it's a bit harder, but the main idea is this first bit. You come up with the parameterization and calculate the Jacobian and rewrite this difficult integral, line integral, into something we already know using the Jacobian factor. Thank you.